Welcome to lecture number 16. This lecture is on substitution and elimination reactions. This particular lecture, there will be probably three lectures in this sequence for this chapter. This particular lecture is on SN2 reactions. But right now, to start off, we're going to just simply overview what the next few lectures will be on. So let's look at substitution and elimination reactions, generally speaking. So we're going to start looking at this reaction here. We have this chlorine attached to a propane chain. Okay, so we could call this 2-chloropropane. And we are adding to this sodium hydroxide. Remember, sodium hydroxide is an ionic compound, where we could say sodium is positive and the oxygen is negative. The oxygen sort of has control of those two electrons that are shared between the two. So if we have O- in this reaction, we have OH-, we can get two different reactions to occur on this 2-chloropropane. We can get an elimination reaction where the chlorine eliminates, it leaves along with a hydrogen to form a double bond, okay? Or we could get a substitution reaction in which the OH replaces or substitutes the chlorine. Okay, so we have two different products that could form. The elimination product, which would be a double bond, or the substitution product, which would be an alcohol. Okay, so those are the two different types of reactions that we can have. We also have sodium chloride and water as byproducts for these reactions. Okay, don't forget about those byproducts if the question asks for them. So we are going to now break down elimination and substitution reactions in more detail. Okay, the first one we're going to look at today is the SN2 reaction, substitution nucleophilic bimolecular reaction. But before we hop into that, let's just answer this one question here. Talk about leaving groups. So we see that for both of these reactions, elimination and substitution, we have this chlorine here. We have this chlorine, which is leaving. Okay, the chlorine is going to leave for both of these processes, through elimination, through substitution. So we need to ask the question, what makes chlorine or any atom a good leaving group? Okay, so let's talk about leaving groups first. So here's a chart showing different leaving groups along with their conjugate acids. Okay, so in order to determine what a good leaving group is, what we have to do is we have to consider the conjugate acid of that leaving group. Okay, so if we consider the conjugate acid of, say, chlorine, okay, we just saw the example before with chlorine. If we look at chlorine here, the conjugate acid of chlorine would be HCl, right, hydrochloric acid, and the pKa of HCl would be -7. Okay, let's look at a bad leaving group. Let's look at something like OH-. That would be considered a bad leaving group. Let's consider the conjugate acid of OH-. That would be H2O, water, which we know is 15.7. Okay, so the good leaving group, chloride, Cl-, has a conjugate acid with a very low pKa, -7, and the bad leaving group, OH-, has a conjugate acid, H2O, of 15.7. It has a higher pKa. Okay, so generally speaking, this is the rule we use when we determine if a leaving group is good or bad. We look at the leaving group, we consider the conjugate acid, and if that conjugate acid has a pKa that's less than 0, then that would be considered a good leaving group. So here we can see a bunch of different leaving groups, I-, Br-, Cl-, this sulfate, as well as water. These are all good leaving groups because their conjugate acids have pKa's less than 0. Conversely, we can look at the bad leaving groups, F-, OH-, NH2-. The conjugate acids of these groups have high pKa's above 0, and so we consider them to be bad leaving groups. Okay, so anytime we see one of these good leaving groups, I-, Br-, Cl-, something like this, those can leave through a substitution or elimination reaction. Okay, so we need to be on the lookout for these leaving groups on the molecules in question. Okay, so for example, let me draw it down here. If we see this molecule, okay, we have a alcohol and we have a bromine on this molecule. Which of these is a good leaving group? Well, Br- would be a good leaving group because HBr has a very low pKa. OH- down here on the left, this would be a bad leaving group. OH- is a bad leaving group because water's pKa is 15.7. Okay, so that's a very quick and easy way to determine if something is going to be a good leaving group or not. So this would be a good leaving group, and this would be a bad leaving group. Okay, so we need to be able to determine quickly and easily which functional groups are going to be leaving groups, and this is the way to do it. Just consider the pKa of the conjugate acid. Okay, so you simply add a hydrogen to it and look at the pKa. Okay. Okay, so we know how to find a good leaving group. Okay, so now let's take a good leaving group and a good nucleophile and learn about the SN2 reaction. Okay, so now looking at the SN2 reaction, SN2 is going to be the most basic reaction that we will learn. Okay, so from here on out in the course, we are going to be studying a lot of different reactions, a lot of different mechanisms. And the SN2 process, the SN2 reaction, is going to essentially be the most basic reaction we can have in chemistry. Okay? So what this stands for is substitution, nucleophilic, and then the 2 stands for bimolecular, meaning that 2 molecules are reacting with each other. Okay? Substitution, nucleophilic, bimolecular. So what happens in an SN2 reaction is we have some sort of alkyl halide, for example, some sort of carbon chain with a leaving group. Here it's just denoted as X. So this could be bromine or iodine or chlorine, for example, just a good leaving group. And we also have a nucleophile. Remember, a nucleophile is typically something that's negatively charged. It's something that can reach out with a lone pair of electrons and make a new bond, okay? So if we have a nucleophile, here we just have NuC to abbreviate nucleophile, so this could be anything. Could be oxygen with a negative charge, could be sulfur with a negative charge, nitrogen with a negative charge, okay? If we have a nucleophile, the mechanism for this transformation is very simple. Remember, we start at the lone pair, okay? We always start with electrons when we draw our arrows. So we start with the lone pair on the nucleophile, and we draw an arrow to the carbon that the leaving group is connected to. Okay, so we draw an arrow to that carbon. This nucleophile is going to make a bond with this carbon, and it is going to kick off the leaving group, hence the name leaving group, right? The X here is the leaving group, and it is going to leave. Now, when it leaves, it brings its electrons with it because the nucleophile is coming in with 2 more electrons. And we don't want this carbon to have 10 electrons, right? It wants 8 electrons. So 2 electrons come in, 2 electrons go out. And what we ultimately get is simply a change from the X being bonded to this carbon to the nucleophile being bonded to that same carbon. Okay. Now we see our leaving group is out here by itself, X minus. Make sure your charge is always balanced. So we start with a negative, we end with a negative. Okay. Now, why does this process happen? Well, up on the top right, I'll draw, if we remember, if we have a carbon and a halogen bonded to each other, we should remember that we have a dipole towards the halogen. The halogen is more electronegative, thus rendering the carbon partially positive and the halogen partially negative. So this negatively charged nucleophile is able to simply come in here and attack this partially positive carbon, okay? That negative charge is attracted to that partially positive carbon, makes a bond with it, and it kicks off the leaving group. So why do we call it an SN2 reaction? Well, you may see the rate equation with regard to an SN2 reaction, and we should remember that the rate for a chemical reaction is simply K, the rate constant, multiplied by the reactants. In this case, we have a halide and we have a nucleophile. Now the reaction rate for an SN2 reaction, if you test it in a lab, if you double the concentration of the halide, you double the rate of the reaction. And if you double the concentration of the nucleophile, you also double the rate of the reaction. So therefore, it can be inferred or it can be deduced that this reaction, an SN2 reaction, requires a collision of both the halide and the nucleophile. If we increase the concentration of either one and the reaction rate increases, it means that there must be a collision between the two happening because we need both of them for the chemical reaction to occur. Okay, if that didn't make much sense to you, that's okay. Just remember that the term SN2, bimolecular, this simply comes from the rate equation because we need both the halide and we need the nucleophile colliding for this reaction to work. Okay, so this would be the rate equation for the SN2 process right here. That's the rate equation for an SN2 reaction, thus the name SN2, because we have these two reagents here. And substitution nucleophilic, indicating this bumping, the nucleophile bumping out this leaving group. So we're substituting the leaving group for a nucleophile. Okay, so there's SN2. Now let's consider something very specific about the SN2 reaction, which can trick some students. This is known as the Walden inversion, and it is only necessary to consider on stereocenters. Walden inversion for SN2. Okay. Now this is important because the SN2 reaction utilizes a backside attack. So let's look at what we mean by that. So I'm going to draw a molecule with some stereo definition here. So I'm going to draw a carbon with 4 different things attached to it, one of which is a leaving group. We should be able to tell from this molecule here what our leaving group is. It would be bromine, because HBr is a very strong acid. So let's combine that with a good nucleophile. Let's take HS minus. Sulfur is just like oxygen. Okay, sulfur is just like oxygen, but it's even a little bit more nucleophilic. We'll talk about why shortly. So we have a good nucleophile here, sulfur, SH minus. This is a good nucleophile. And we have a good leaving group in bromine. Okay, bromine is a good leaving group. So let's go ahead and draw our SN2 reaction, but I'm going to draw the arrow a little bit differently here. Instead of drawing like this, directly to that carbon and then kicking off the leaving group, I'm going to draw it a little bit more accurately by showing a backside attack, where the nucleophile comes in on the backside of the leaving group and forms a bond on the opposite side of that carbon. Okay, this is the backside attack. And it's very important when we have a stereocenter like this. Why is it important with a stereocenter? Well, let's draw the product of this reaction. So our sulfur is now over here, made a bond. We have ethyl, we have methyl, and we have this hydrogen here. And our byproduct is Br minus. That's what got kicked off. That's our leaving group. Okay, so that would be the product of the reaction. Now the backside attack is important because if you can't see just by looking at it and you need to do the con-angle pre-log system, that's just fine. But if you do denote these R or S configuration, we actually start off with one configuration and end up with another. So we start with the R configuration here, and we end up with the S configuration here. We get inversion of stereochemistry. The SN2 gives inversion of stereochemistry due to the backside attack. So the nucleophile comes in from the backside and makes a bond on the opposite face of that carbon. So when the leaving group leaves, we are left with the inverse stereochemistry. If we start with R configuration, we end up with S configuration. Okay, so remember that we get this inversion of stereochemistry with the SN2 reaction. You can think about it sort of like an umbrella flipping backwards in the wind. If you have an umbrella and it blows really strongly in the wind, the umbrella sort of flips, it inverts. So the same thing happens with organic molecules like this. We have this sort of umbrella shape. Let me do it in blue here. We have this sort of umbrella shape of these three groups. The nucleophile comes in and forms a bond there, and the umbrella shape sort of flips, just like an umbrella blowing out in the wind. Okay? It's really important to be able to visualize the tetrahedron for these types of processes. So this doesn't really affect if we have a molecule like this up on the top. Now, if we get nucleophilic addition here on a primary bromine, it doesn't really matter because it's not a stereocenter, so we just end up with a primary nucleophile. So the only time we have to consider this backside attack in this inversion of stereochemistry is if we have a stereocenter with the leaving group. Okay, if the leaving group is attached to a stereocenter, that's when we need to be cognizant of this inversion of stereochemistry occurring at that carbon. I'm going to draw a transition state for the reaction down here. Maybe I will actually erase a little bit of this to make more space. So for the transition state, I'm going to draw this here. We have this carbon, and that carbon has the bromine on it. That's the leaving group. Now I'm going to put a dotted line here for the bromine because the bromine is sort of getting kicked off at the same time that this sulfur is coming in. So there is a point in time when this carbon is sort of halfway bonded to sulfur and halfway bonded to bromine, right? This sulfur is coming in, this sulfur is coming in, and this bromine is getting kicked off, okay? Now this carbon is also connected to a methyl group and a hydrogen and an ethyl group. And these three groups here are sort of in the same plane. They're sort of in the same plane of each other. You can think of a trigonal planar structure for these. And then the leaving group and the nucleophile are on opposite sides of that flat trigonal planar structure. Okay, so this is what the transition state would look like. And when we consider transition states in chemistry, we put brackets around them and then this double dagger. So this is a representation of the transition state of an SN2 reaction. Again, the nucleophile here, SH, is coming in to form a bond, and bromine, the leaving group, is leaving. So there's a point in time when these are both sort of halfway connected to carbon, okay? This is not a compound you could isolate. You cannot isolate transition states. It's just a representation of what's happening on a molecular level. Okay, that's an important distinction to make. But hopefully you can see why we get inversion of stereochemistry now because of this backside attack. Okay, due to the fact that we get a backside attack that causes the stereocenter to flip or invert. So if we start with R, then we go to S, and if we start with S, then we go to R. Okay, so that's an important thing to remember for SN2 reactions. So what we have here now is we have this chart, this table, showing the relative rates of reaction based on the substituents that we have at either the alpha or beta position. So what do we mean by alpha or beta position? Let me take a brief aside here. And let's consider this structure that I've drawn right here in black. We have a 3-carbon chain with a leaving group on it. I just drew X for a generic leaving group. Now, if we want to consider the other carbons in the chain, the other positions that we have, relative to this, right? This is our leaving group. This is the interesting part of the molecule. If we want to consider the other atoms in this chain, what we do is we use the Greek alphabet and we simply work down the chain, giving each atom a different letter of the Greek alphabet. So the next carbon down the chain, if we want to discuss this red carbon here, rather than saying, oh, the carbon right next to the leaving group, we would say the alpha carbon. And if we wanted to say this carbon right here, we wouldn't say, oh, the carbon that's 2 atoms down. We would simply say the beta carbon. And then we would go gamma. And then we would go delta. And we would simply work down the whole Greek alphabet. Instead of saying, oh, it's the 3rd carbon away from the leaving group, we would just say the gamma carbon. Okay. So in this course, we will really just be discussing the beta and the alpha positions, but we may see other gamma or delta, for example. But what we say when we mean alpha carbon, it simply means the carbon next door. Beta carbon means 2 carbons away, okay? So if we look back with that information in mind, look back at this chart here, and we see on the left side of the chart, we see the effect of the alpha substituents. We have different structures, and then we have their relative rates. Now, the relative rate that we put as 1 would be the primary bromide, right? Ethyl bromide. It's a primary bromide. We've given that a relative rate of 1. The methyl bromide, just above it, has a relative rate that is 145 times faster. If we look below the primary bromide and we see the secondary and tertiary bromides, the secondary bromide is much more slow. It has a relative rate of 0.008. And the tertiary bromide is so slow that there's essentially no reaction. It's negligible rate. Okay. So that means as we increase the substitution at the alpha position, the reaction gets much, much slower. If we look on the right side of the chart, we see that the beta position also has an effect, but not as strong of an effect. Okay. If we have substitution at the beta position, we do slow the reaction down as we increase that substitution, but it's a slightly weaker effect than at the alpha position. Now, why is that? So this is because of sterics. Sterics is incredibly important in chemistry. Sterics. This is incredibly important, especially for chemical reactions. A lot of reactions are dictated by sterics, and I did mention this in a previous lecture, but if you don't recall, sterics is essentially the bulk associated with a molecule or atom. Okay, the bulk associated with a molecule or potentially a portion of a molecule. And so, simply put, sterics just means that things are getting in the way. If we consider a primary leaving group, like this one here, a primary leaving group is much more reactive to a nucleophile because there's simply more space out here where it can make a new bond. If we compare that to a tertiary bromide, we can simply see that there's less space here for this lone pair to come in and make a new bond. See how there's all these other carbons in the way? So it makes it much harder for that SN2 reaction to take place simply because things are in the way. Okay, so sterics is just a fancy word for saying bulk, or the tendency of groups to get in the way of a chemical reaction from occurring. Okay. So simply put, if that didn't make any sense, let's summarize it very simply, and we will say that this is the trend for reactivity for SN2. Let's put reactivity of SN2. The most reactive is going to be the methyl leaving group, followed by the primary, followed by the secondary, followed by the tertiary. And it should be noted that the tertiary essentially does not happen. We can sort of keep that as a little aside here. SN2 typically does not occur on tertiary leaving groups. Okay, so the fastest type of reaction would be if we have a methyl leaving group, so just CH3 with a leaving group, that would be the methyl. A primary is if we have something like this, right? The leaving group is connected to one other carbon. A secondary would be if the leaving group is attached to two other carbons. The carbon that the leaving group has is connected to two other carbons. And then a tertiary is when that carbon is connected to three other carbons. Okay, so the methyl is going to be the fastest, followed by the primary, followed by the secondary, followed by the tertiary. Okay, this is the reactivity trend for SN2. And you should also remember to be aware of the beta position. Okay, so this is obviously all on the alpha carbon, which we'll put in red here. The alpha carbon, that's the substitution pattern on the alpha carbon. And there's the same trend for reactivity at the beta carbon. Okay, if we have a primary carbon at the beta position, it'll be faster than if we have a secondary carbon at the beta position. Okay, just remember that the alpha position has a stronger effect because the alpha position is where the reaction is actually happening. So if we have a lot of steric bulk around the reaction center, a lot of different things getting in the way, hopefully we can see why that would be a slower process. Okay. So now let's look at a couple simple examples just to make sure we understand the SN2 reaction and the mechanism associated with it. So let's look at these two examples and draw a mechanism and predict the product for SN2 reaction. Now these should be pretty simple since SN2 is a very simple mechanism and it's telling us exactly what to do. So we have a nucleophile, which is going to be a negatively charged molecule. And then we have a good leaving group. In this case, it would be iodine, I-. Remember, I- is a good leaving group because HI, hydroiodic acid, is a very strong acid with a negative pKa. So let's take our nucleophile, the negatively charged molecule, and come in with a backside attack and kick off that iodine, kick off that leaving group to make a new bond. What would that look like? Well, we have a 3-carbon chain. Now this 3-carbon chain is connected to an oxygen, which has 2 carbons and a carbonyl on it. Our byproduct would be I- because we just kicked it off. And that would be the reaction. That would be the product for this SN2 reaction. Okay, so we start with our nucleophile, our negatively charged molecule. We come in on the backside of this carbon that has the leaving group. We kick off the leaving group. Okay, and we make a new bond to that carbon from the nucleophile to that carbon. And here's our leaving group, I-. Okay. What about for this one down here? We have Na plus and OH minus because that's an ionic compound. Now OH minus is going to come in here. I'm going to actually draw OH minus right over here because I like to draw my arrows starting from a lone pair here. I like to put the negative charge up above, but always draw your arrows starting from a lone pair because arrows show the movement of lone pairs. Our nucleophile is going to come up and attack this carbon because this carbon has a leaving group on it. This is a partially positive carbon, right? Because it's polarized towards the leaving group. Okay. Our nucleophile attacks that partially positive carbon and our leaving group is kicked off. And that would be the SN2 reaction. We substitute out the chlorine for the oxygen. So our final product would be simply the same carbon chain, but instead of a chlorine, we now have an OH. And then we have our byproduct, which is Cl, and we also have sodium, so it would be NaCl. Sodium chloride would be our byproduct. Okay. So these are very simple SN2 reactions. If these didn't make sense, practice a few more on the internet. Make sure you have these down because the other mechanisms we will look at will be a little bit more complicated than these. And also remember, if you do have a stereocenter for an SN2 reaction, you have to really remember that inversion of configuration. That's always a trick question on exams that you have to look out for, okay? In this case, we didn't have any stereocenters, so the inversion ultimately didn't do anything for us. We still get the backside attack, we still get inversion at that carbon, but if we don't have a stereocenter, the inversion doesn't mean anything, right? Okay, so just to finish off our lecture on SN2, let's consider for a second what makes a good nucleophile. Okay, we know for an SN2 reaction, we need a good nucleophile, and then we need some carbon that has a leaving group because that nucleophile is going to replace or substitute for that leaving group. Okay, so what makes a good nucleophile? A good nucleophile is something that typically has a negative charge. Okay, something that has a negative charge. So if we were to compare, for example, H2O versus OH minus, OH minus would be a better nucleophile than water because it has a negative charge. So if we have a negative charge, we are going to have a better nucleophile, okay? The other thing that we should consider is the polarizability And polarizability is composed of two things. It's the atomic size as well as the number of electrons that we have. So when we think polarizability, you should be thinking down and to the right on the periodic table. Down because we increase our atomic size going down, our atomic radius, and to the right because we increase the number of electrons that are in each shell, right? So down and to the right, we're going to have our more polarizable atoms. You should think, when you think of polarizability, you should think things like iodine, like bromine, things like this are very polarizable, okay? And remember, polarizability is important for nucleophilic strength because when we have a large electron cloud around iodine, for example, and we have all these electrons floating around, there is a chance that we get more electrons on one side than the other. So this portion of the molecule where there just happen to be more electrons at one given time could be more negative, and this side over here could be more positive. So the larger atom that we have with the more electrons in it, the more of a chance we have for these fleeting dipoles to form in a molecule, okay? So this would be polarizability. Okay, so let's draw out some good nucleophiles and some weak nucleophiles. If you'd rather just memorize these just to get through the course, that works too. Strong nucleophiles. This is going to be things like I-, Br-, Cl-, Rs-, so a sulfur with some carbon on it, or just sulfur with a hydrogen on it, negative charge. OH-, could be oxygen with carbons on it also, RO-, or Cn-, that would be like this, nitrogen triple bonded to carbon with a negative charge, the cyanide. This is a very good nucleophile as well. This carbon is negatively charged. It's also quite small, which allows it to pierce the shells quite easily and get access to that carbon. Okay, so this is a very good nucleophile. Weak nucleophiles, on the other hand, these would be things like water, H2O, or an alcohol, ROH. Okay, so these would be things that they don't have a negative charge, they're not very polarizable. Okay, these would be weak nucleophiles. Okay, and finally, we'll just cover quickly the solvent effects on SN2 reaction. SN2 reactions, simply put, prefer polar aprotic solvents. I have a little chart here showing aprotic and protic solvents. The key distinction between aprotic and protic is that protic solvents have hydrogens attached to electronegative atoms such as oxygen or nitrogen, and polar protic solvents such as ethanol with that OH bond are going to hinder the SN2 reaction from occurring because those protons are going to get in the way of the reaction. Okay, so that's SN2. This is probably the most basic reaction that we'll study, simply displacing a leaving group with a nucleophile. But we will continue with another type of substitution, SN1, as well as the elimination reactions, E1 and E2. And then we'll summarize these all up and do a workshop. So we will get much more practice on this topic. Okay, the next lecture will be elimination E2 reaction.